In example 5, we have a single bay, single story portal frame that has two hinges internally in it, and it has a fixed end support at the lower left and a pin support at the far right. We're asked to find the shear, moment, and qualitative deflected shape diagrams for this particular frame, given the load and given the reaction values that have been provided to us. We're going to demonstrate those in 3 parts. The first part will just be to find the member end forces, and then we'll do the other pieces as we go along. So note that we do have a statically determinate system. We've got a frame, meaning each of these member pieces are members that either have transverse loads or otherwise are responding to the applied loads through bending. And in this external viewpoint, then we've got 1, 2, 3 potential reaction components at the left, 2 potential ones at the right, total of 5 for the unknowns for the global perspective. And then the number of equations that we have to deal with are 3 equilibrium equations plus 2 conditions associated with the hinges. So 5 equaling to 5, 5 unknowns, 5 equations. That's going to make that statically determinate. Even though the moment here at A turns out to be 0 for the reaction, doesn't mean that we can't get rid of that moment. Indeed, that in this case actually we need that moment for stability. If this was a pinned end and a pinned end for the 2 supports and we pushed on the side, this thing would rotate right on over sideways. So we do need this there, even though in this particular load case we have a 0 moment. Let's first take these reactions and these applied loads, break up all of the pieces here. The columns will break right above the support, right below the joints, both places there, and this horizontal beam all the way across will break at the hinges. And when we do that, then we've got all these little tiny pieces, the joints here, we've got down here at the reactions, the columns, and we certainly have potential shear and axial forces all sprinkled all the way through. We don't have an arrow showing yet, and I haven't shown the bending moment. Let's start with the simple segment, that's EF over here at the right. It's the simplest because it has the simplest set of reactions and its connection up at the top. Nice and simple. We've got, from the axial case, a 20 kip compressive force here, and we can go ahead and then flip that right onto the joint. Notice then we can flip that into the shear on that segment. There's another 20, still the same, and then we'll flip that again over here on that little beam segment right there at the joint as well. So there's our 20. We're not going to go any further because now we pick up some load on that little segment DE from the joint over to the hinge. So we'll leave that for now. Come back to the column. We've got the 6.25 acting to the left at joint F, and since there's no other transverse loads applied to that member, that means that the shear at the top has to be 6.25 as well. Now the thing is that when you look at that that column and those 2 shears, we end up with then a clockwise couple, and so we're going to need to resist that with a moment that would be equal to 6.25 times our 12 feet for kip feet, and that would be 75 kip feet for that bending moment at the top of the E end of that column EF. So then you flip that, right? That's a counterclockwise resisting moment, so on the joint we effectively have a clockwise 75 kip foot. On the other side of the joint, then, for equilibrium, you have to oppose that with 75. And then we sprinkle that all the way around, again, flipping it. Now, the one thing we didn't flip was the 6.25 shear, so let's get that in and turn the corner on the joint for lateral equilibrium. Then we have another 6.25 for that axial force, and then we'll be able to follow that all the way through. And each of these beam segments, flipping it each and every time, we've got this compressive effect that's going all the way through, and then that shows up all the way down here becomes shear at the top of column AB, and then gets flipped again, and notice we'll have equilibrium of that column. So that's good. While we're here, we can also do the axial force. 20, there's another 20, becomes shear when we turn the corner, another 20, turn it around again, and we've got that 20. So let's go back and now look at column AB. I'm trying to avoid dealing with the beam segment here. Deal with the simplest things first. 6.25 again times 12 will give us, this time, a counterclockwise moment. So we need to resist that with that same 75, same math that we had over here in the other column. Flip it, and flip it again. And we got 75 there. Okay, so now it's time to tackle these inner pieces. Right now we know, or we should anticipate, that there might be some, oh wait a minute, there better not be a moment at C because that's a hinge. Alright, if that's the case, then let's take a look here. Then this CD segment is really a simply supported segment, pin, pin, no moments there, and so that shear at the left is going to equal the direction and magnitude of the shear over at the right, as in acting up. We're going to split the total load. 2 times 10 is 20, and we'll split that. That will be 10 and 10 for the shear. Let's see if this is going to work out right. Because then you flip your shear over here on the other side at D. We'll have 2 times 5 feet, that's 10. 10 plus 10, all both acting downwards. Oh, well, hey, that was going to be opposed by the 20 acting upwards on the right. So that worked out correct, and we'd have the same situation happening over at the other side. And now the only thing we have to be aware of is, hey, do we really end up with 0 moment at D like we're supposed to? So let's see what we have. We have 2 kips per foot times 5 feet times its moment arm of 5 halves, right? That would be, oh, I should write this as sum of moments about point D. Let's take clockwise as positive, so 2 times 5 halves, and then we got opposing that minus 20 times 5, and then we've got plus 75. That equals, that's 25 minus 100 plus 75. That equals 0 numerically, and that's what it's supposed to. So that's good. That means we got that correct, and it means this other one is going to work out because it's just the flip of the same thing. So there's our member end forces, and now we can go do shear and moment diagrams.